In this section, we're going to be talking about weak acids. Now, the generic formula for a weak acid is the following. So notice HA is your weak acid. If it reacts with water, it's going to form hydronium ions plus your anion. Now notice I have the double arrow, and the reason why is because not all of the weak acid is going to dissociate. Another way of writing this, which is actually the way that I prefer to write it, is your weak acid is going to dissociate to form simply your hydrogen ions plus your anion. So notice the only difference is in the second one I haven't included water, and instead of hydronium I put the hydrogen ions. But keep in mind, hydronium and hydrogen ions, those are synonymous. So I actually prefer to use the second equation. Let's really quickly make sure we understand the difference between strong acids and weak acids from a molecular perspective. If you look at the acid on the left-hand side, the strong acid, what you should notice about the molecules is that none of the strong acid exists anymore. It is all dissociated into hydronium ions and your anion. For the weak acid, however, if you look at the molecular view, you have not only your anion and hydronium ions, but you also still have your weak acid present. So that's why you need the double arrow. That's why you do not simply have one arrow moving towards the right-hand side like you do with strong acids. And so this is going to largely affect our ability to calculate values such as pH or Ka, as you'll learn about in this section. So looking back at the reaction for a weak acid, I can then write the equilibrium expression. Specifically, I would put the concentration of hydronium ions and your anion on top, and then I would put the concentration of your weak acid on bottom. Remember, we ignore water because it's a pure liquid. Now this is the equilibrium expression for an acid, therefore your Ka we call your acid dissociation constant. So now at this point we have Kw, we have Kc, we have Kp, and now we've added Ka, the acid dissociation constant. One important fact that you need to remember is the fact that the larger your Ka, the stronger the acid is. And that makes sense because the larger your Ka, the larger the concentration of your dissociated ions. So a strong acid would have a very large Ka because it would have no acid left over. Instead, it would be purely the ions. So in this example problem, I'm told the concentration of my weak acid, and I know the final pH. Now, assume that the final pH is a representation of the concentration of your hydrogen ions at equilibrium. And so the first thing that I actually need to do is I need to write the equilibrium reaction for the dissociation of this weak acid. So specifically, the formula, the reaction is going to be your weak acid dissociating into its ion, so H plus and CHO2 minus. Now, since this is a weak acid, I need to write an ice chart, and then I'm going to just plug in all the values that I already know. I know that my initial concentration of my weak acid is 0.1, I'm going to write 0 molar. My initial concentration of my hydrogen ion is 0, and my initial concentration of this ion is 0 as well. I know stoichiometry-wise that this is going to lose, the change is going to be a loss of that acid by X. This is going to gain by X, and that's going to gain by X as well. Okay, so I know that my equilibrium concentration of my acid is going to be this, hydrogen, and that. Now, the other piece of information that I know is that my pH is 2.38. So since I know the fact that my pH equals the negative log of my concentration of H+, what I can actually do is I can plug in my pH into this equation to calculate the equilibrium concentration of my hydrogen ion. So I know my pH is 2.38. And I'm actually going to move the negative over here. So the negative 2.38 equals the log of my concentration of H+. Keep in mind, since nothing is written here, there's implied right here to be a base 10. So to calculate the concentration of hydrogen ions, it would just be 10 raised to the negative 2.38, and that equals my concentration of H+. And what I find from my equilibrium concentration of H+ is that it's 4.2 times 10 to the negative third. So I now know my X. It's 4.2 times 10 to the negative third. Same thing here, 4.2 times 10 to the negative third. And here, if I take 0.10 and subtract 4.2 times 10 to the negative third, if I'm rounding for significant figures, actually, when you actually calculate that, it ends up just being 0.10 molar. So if I want to find my Ka, that is simply going to be the concentration of my hydrogen ions times the concentration of my anion all over the concentration of my weak acid and now I just have to plug in values. I know that the concentration for both of these is 4.2 times 10 to the negative third, and since there are two of them, I'm just going to square this value. And I'm now going to divide that by the concentration of my acid, which is 0.10. And so what I end up getting for my Ka value is 1.8 times 10 to the negative fourth. Now, your percent ionization, that is equal to the concentration of your ionized product divided by the concentration of the original substance. So the concentration of your original. So what percent of your original substance was actually ionized? Then you're going to multiply that by 100. So in this case, the concentration of my ionized substance is 4.2 times 10 to the negative third. Molar. The concentration of my original substance is 0.10 molar. Now I'm going to multiply that by 100%. What I end up getting is 4.2% of my original substance was ionized. In the previous problem, you were asked to calculate the Ka, the acid dissociation constant, when given pH. In this problem, it's the exact opposite. You're asked to calculate the pH when you're given your Ka. And so we're going to use the same technique, except you're going to be solving for something different. So it's going to change the problem ever so slightly. So here it tells you that you have 0.30 molar acetic acid, and it has a Ka of 1.8 times 10 to the negative fifth. So it asks you to find the pH. Well, the first thing you need to do is you need to write the formula or the reaction for this acid dissociation. So I'm given acetic acid, okay, and it's going to dissociate into its ions, so hydrogen ion and acetate. Next, I need to write my ice chart. So ICE, I actually know my initial concentration of my acid, it's 0.30 molar. I know my initial concentration of hydrogen ions, it's 0, and acetate ion, it's 0 as well. Now I know the change that occurs, it's minus x. I know that this is plus x. And I know that this is plus x. So I'm going to find my equilibrium concentration, so 0.30 minus x. This one here is just going to be x, and this one here is going to be x. The next thing I need to do is I need to write my equilibrium expression. Well, I know that Ka equals x times x, so that's x squared, all over 0.30 minus x. Now I need to solve using Ka. Well, I know that Ka is 1.8 times 10 to the negative fifth. And if you have an equilibrium constant that is that small, we're going to make an assumption. Before, we had to solve for x using the quadratic formula, which can be very time consuming. If you have a very small k, we're going to assume that it will have no effect on the change in the concentration of acetic acid. Like in the previous problem, it had no effect on the concentration of your weak acid. Therefore, we're going to ignore your x. We will need to check to make sure that was an appropriate assumption at the end of this problem, but let's assume that right now, and let's solve for x. So when I multiply 0.3 by your 1.8 times 10 to the negative fifth, what I get is that x squared equals 5.4 times 10 to the negative sixth. I now need to find the square root of that, and what I find is that my x, that equals 2.3 times 10 to the negative third molar, because I'm talking about concentration, which means that my concentration of my hydrogen ion, since that is x at equilibrium, that equals 2.3 times 10 to the negative third molar. And so what I can do to solve for pH, because that's what it's asking me to do, is I can just find the negative log of 2.3 times 10 to the negative third, and that will give me my pH. And so what I end up getting is that my pH equals 2.64, or just 2.6 using the correct number of significant figures. Now the important thing for you to know is when I'm done, I've got to check my assumption. So check the assumption that I can just ignore this x. Polyprotic acids are acids that have more than one hydrogen that can be ionized. So if you look at this example here, if I start off, I have H2SO3. Notice I have two hydrogens. So for the first reaction, I lose the first hydrogen ion to produce HSO3 with a -1 charge. Then I can lose another hydrogen producing hydrogen ions and SO3 2-. Notice the difference in your acid dissociation constants, however. So your Ka1 is larger than your Ka2. Well, let's make sure we understand why. Keep in mind that as soon as you've removed a proton from an acid, that acid now has a negative charge. So it makes sense electrostatically that it would require more energy and therefore be harder to dissociate the second proton, therefore resulting in a lower Ka2 because less hydrogen ions and SO3 2- ions are going to be able to be produced. And so this difference in Ka1 and Ka2 simply results from the fact that it's easier to remove the first proton than the second proton. Okay, so that's just a rule to keep in mind for polyprotic acids, that it's always easier to remove the first proton from a polyprotic acid than to remove a second one. So in problems that we're considering, if we're asked to find the pH of an acid that's a polyprotic acid, we will actually ignore the concentration of hydrogen ions that are produced in the second reaction and instead simply concentrate on the hydrogen ions that are produced when the original acid dissociates into its ions. Now this problem is only slightly more complicated than the ones that we previously solved because carbonic acid is actually a polyprotic acid. So we need to write the equilibrium reactions for not only carbonic acid losing its first proton, but then also its second. So I'm going to write those right here before we get started. You've got H2CO3, which is a weak acid, and it's going to dissociate to form hydrogen ions and HCO3. Now, HCO3 can then go and lose the other proton. Remember, it's harder to do because it's now negatively charged, but it can. and it would form carbonate with a 2- charge. So I've got these two dissociations, and what this question is asking me is what is the pH of a solution, of carbonic acid solution, if its concentration is 0.0037 molar. Then it also asks what's the concentration of carbonate, what concentration is going to be produced. So for the first one, because my Ka1 is much larger than my Ka2, to find pH, I'm actually only interested in the concentration of this hydrogen, because the amount of hydrogen ion that's produced here is going to be much less than here, and therefore it's only slightly going to alter my pH if I don't consider this concentration of H+. So I'm only going to consider this H+ right here. So what I'm going to do is create an ice chart. I know the initial concentration is 0.0037. I know the initial concentration of hydrogen is 0. HCO3 is 0 as well. So I'm going to subtract X. I'm going to add X. Okay. And since I know my Ka1, I'm going to plug these values into my equilibrium expression. My Ka1 equals the concentration of hydrogen ions times the concentration of HCO3 all over the concentration of carbonic acid. So I'm going to plug in all my values now. 4.3 times 10 to the negative 7th is my Ka. 1 times, I'm going to just say X squared because it's hydrogen and HCO3 concentrations, which both are X, and 0.0037 minus X. Since my Ka is so small, I'm going to ignore this X for right now. And so when I solve, I get that X squared equals, or 1.6, rounding properly, times 10 to the negative 9th. And so when I solve this, I find that my X equals 4.0 times 10 to the negative 5th molar. Okay? And from that, since this is also the concentration of my hydrogen ions, because that's just X, I can just find my pH quickly by taking the negative log of 4.0 times 10 to the negative 5th. And what I end up getting is 4.4 for my pH. Okay? Keep in mind the fact that I'm just using this concentration of H+, not the hydrogen ion that's produced in the second ionization of this acid. So now what I can do, I need to calculate for my concentration of CO3 of carbonate. So I'm now going to use this second reaction. I need to use an ice chart again to calculate my equilibrium concentration of CO3. I know the initial concentration of HCO3 is simply 4.0 times 10 to the negative 5th because that's my X. So is the concentration of hydrogen ions. And I know my initial concentration of carbonate is 0 molar. So I'm going to subtract X from here. I'm going to actually add X to here. So this is new. Add X here. So I end up with 4.0 times 10 to the negative 5th minus X. Here 4.0 times 10 to the negative 5th plus X. And then this is just X. So I'm now going to plug in these values into my Ka2, which equals the concentration of H+ times the concentration of CO3 2-, all over the concentration of HCO3 minus. And so what I find out is that my Ka2 is 5.6 times 10 to the negative 11th. That was given to me. I know my concentration of H plus is 4.0 times 10 to the negative 5th plus X. I'm going to make the assumption that X will not influence that value. I'll need to check that at the very end, but instead of writing 4.0 times 10 to the negative 5th plus X, I'm just going to write 4.0 times 10 to the negative 5th. And I'm going to multiply that by the concentration of carbonate, which is just X, and I'm going to put that over the concentration of my acid, 4.0 times 10 to the negative 5th. Again, I'm not going to include the minus X, and I'll just check the validity of that at the very end of this. Well, I find that these cancel, which leaves me with the value of X equals 5.6 times 10 to the negative 11th. Well, X is my concentration of carbonate. Therefore, my concentration of carbonate equals 5.6 times 10 to the negative 11th molar.